This is electric field example number 3, and we've got Topeka pulling her wool sweater over her head, which then charges her body as the sweater rubs against her cotton shirt. First thing they want us to do is figure out what is the electric field at a location where a 1.6 times 10 to the negative 19th Coulomb piece of lint experiences a force of 3.2 times 10 to the negative 9th as it floats near Topeka. So we've got this little piece of lint over here, and that little piece of lint has a charge. So here's our lint, Q equal to 1.6 times 10 to the negative 19th coulombs. And we know that the force on that particle is approximately equal to 3.2 times 10 to the negative 9th newtons. So we've got all the givens that we need. They want us to find the electric field. Remember, electric field E is equal to force divided by that charge, which is Q. Sometimes you'll see they'll use a little O there, or sometimes they call that a naught, in order to signify that's the test charge. So the force is 3.2 times 10 to the negative 9th newtons. We're going to divide that by our charge, which is 1.6 times 10 to the negative 19th coulombs. If you do your math, you should end up with 2 times 10 to the 10th newtons per coulomb. For letter B, they want to know what will happen if Topeka now touches a conductor like a doorknob. Well, what she'll do is she will just ground herself, and there would be that spark that would go from one place to the other. So that is example number 3. Let's go ahead and go on to example number 4. This one is about a fly who accumulates 3 times 10 to the negative 10th coulombs of charge. Our charge then, of course, here is equal to, so Q is equal to 3 times 10 to the negative 10th coulombs. The other thing that they tell us is they want to know if you are standing or if there's something at a distance of 2 centimeters away from the fly. They want to know what is the magnitude and the direction of the electric field. This should be equal to 0.02 meters. You've got to make sure everything is in meters, kilograms, coulombs, just basic units. So let's go ahead and solve the rest of this one. E, we remember electric field, can be equal to a couple of different things. In the last problem, we said it was force over the charge. But in this one, we do have charge, but now we have a distance. So we're going to use a different equation instead of this one. We're going to use E is equal to K times Q, and then that's all over D squared. K, remember, is 9 times 10 to the 9th. Q in this problem was 3 times 10 to the negative 10th coulombs, and then we need to divide that by our distance, which is 0.02 meters, and we do need to square that. When we're done, we're going to have an answer of about 6,800 newtons per coulomb, and the direction is always indicated by the sign on the charge, and because there's no negative sign here, we're going to assume it's positive, and we know that anytime you have a positive charge, the electric field always points away. And that is the end of examples number 3 and 4.